Urine formation occurs continuously in the kidneys. It involves three main processes that take place in different parts of the nephron. The processes involved in the formation of urine are glomerular filtration, tubular reabsorption, and tubular secretion. Urea is formed in the liver by the urea cycle. The urea so formed is removed from the blood by the kidneys and becomes a component of urine. The fluid with dissolved waste substances so formed in the kidneys is removed from the body as urine. It is a transparent yellowish fluid which consists of water and metabolic wastes such as urea, uric acid, creatinine, and hippuric acid. It also contains sodium chloride, vitamin C, pigments, and, where they have been ingested, drugs. An adult healthy man passes about 1 to 1.8 liters of urine in 24 hours. Urine formation begins with ultrafiltration of blood through the walls of glomerulus and Bowman's capsule. The efferent arteriole is considerably narrower than the afferent arteriole, resulting in high blood pressure in the glomerular capillaries, which force the fluid constituents of the blood into the capsular space or the lumen of the Bowman's capsule. The epithelial cells of Bowman's capsule, called podocytes, are arranged in such a manner so as to leave some minute spaces called filtration slits or slit pores. Also, the endothelium of the glomerular capillary has minute pores. The slit pores in the Bowman's capsule and the pores in the capillary allow almost all the constituents of the plasma to pass into the capsular space. The basement membrane acts as a filter and prevents the larger molecules like the blood cells and the proteins in the blood to pass through. As blood passes through the glomeruli, much of its fluid containing both useful chemicals and dissolved waste materials moves out through the membranes and then flows into the Bowman's capsule. This process is called glomerular filtration. Glomerular filtration is a passive, non-selective process. The filtrate so formed is called the glomerular filtrate. The glomerular filtrate mainly consists of water, sodium ions, potassium ions, glucose, amino acids, and urea. The amount of filtrate formed by the kidneys per minute is known as the glomerular filtration rate, GFR. If the glomerular filtrate were to be excreted from the body unchanged, the person would be in danger of dehydration and starvation. To avoid this, water and other useful materials are reabsorbed from the glomerular filtrate and only a small volume of concentrated urine is formed. During reabsorption, the molecules move out of the tubules and return to the blood through the peritubular capillary. Reabsorption occurs within all three regions of the nephron and in the collecting duct, but most of it takes place within the proximal convoluted tubule or PCT. The cuboidal epithelial cells of proximal convoluted tubule have numerous microvilli which increase the surface area available for reabsorption. Glucose and amino acid is actively transported out from the cells of the PCT. Water flows out by osmosis. Certain chemicals in the blood that are not removed by glomerular filtration are removed by a third process of urine formation called tubular secretion. These chemicals are removed from the blood in the peritubular capillaries to the renal tubule by both passive and active transport. These chemicals enter the PCT or the DCT and get mixed with the glomerular filtrate and are eliminated from the body. Chemicals removed by tubular secretion are those ions and molecules that are toxic to the body at elevated levels. Ions like K+, H+, NH4+, are removed from the blood by active transport into the filtrate in the DCT. The molecules like creatinine, pigments, medicines are also secreted actively into the filtrate in the PCT. Mammals and birds have evolved a mechanism to excrete hypotonic urine for conserving body water, which is necessary for land life. This mechanism, called counter-current mechanism, refers to a system in which the inflow runs parallel to, counter to, and in close proximity to the outflow for some distance. In kidney, the structures which form the counter-current system are the loop of Henle and vasa recta. The osmolarity of the renal medulla goes on increasing progressively with depth from 300 milliosmol per liter to 1200 milliosmol per liter. This medullary gradient is generated by the loop of Henle of the juxtamedullary nephrons. Vasa recta help in maintaining the medullary gradient. As medullary interstitium becomes hyperosmotic due to accumulation of solutes from the ascending limb of loop of Henle, water osmotically comes out of the descending limb of the loop of Henle. The fluid in the descending limb of loop of Henle becomes hyperosmolar as it turns round the hairpin bend to enter the ascending limb of loop of Henle. As the descending limb of vasa recta goes down into the medulla, it loses water and gains sodium chloride, whereas as it ascends it gains water and loses the sodium chloride. Thus there is no net gain or loss of fluid and solutes in the vasa recta. As the ascending limb of the loop of Henle is impermeable to water, the fluid reaching the DCT is less concentrated than the plasma. The end part of the collecting duct allows passage of urea into the medullary interstitium. This amplifies the medullary osmotic gradient. As the collecting duct descends from cortex to the tip of renal medulla, more and more water moves out by osmosis due to the medullary concentration gradient established by the counter-current mechanism. Thus, urine is concentrated by this mechanism. Urine is produced and drained continuously by the nephrons into the renal pelvis. From renal pelvis, it is carried down by the ureters to the urinary bladder, from where it is expelled out through the urethra. The process by which the urine is expelled from the bladder through the urethra is known as micturition or urination. Urine is stored in the urinary bladder till a voluntary signal is given by the central nervous system. Normally, when the bladder is relaxed and filling, both internal and external sphincters are closed to prevent urine from dribbling out. As the bladder fills, the stretched receptors of the urinary bladder send signals to the central nervous system. The central nervous system passes on motor messages to the smooth muscles of the bladder to contract. Simultaneously, the internal and external sphincters relax, causing the release of urine. The neural mechanism causing micturition is known as the Micturition Reflex.